Year 12 and happy new year to you all. So you should be in a double physics with me now this morning, Monday morning, January the 4th, and you're not, you're still in bed. And you've probably just got a ping on your phone asking you to get out of bed and have a look at my online lesson, which this is about momentum, our next big topic. I imagine you met momentum in GCSE. The momentum of an object is the product of its mass and velocity. If you look at the examples at the top there, you wouldn't want to be in the way of a charging elephant or a speeding bullet. Both have very high values of momentum. The elephant because it has a great mass, and the bullet because it has a great velocity. Okay, the units of momentum are kilogram meters per second. And we'll also talk about how they're related to Newton's laws. So the most basic of examples there, calculate the momentum of a car. If its mass is 1,000 kilograms and it's moving at 60 meters per second, you multiply the mass and the velocity and you get a momentum of 60,000 kilogram meters per second. Phew. So what I'd like you to do, please, is have a look at these basic 6 questions here to start. They are quite basic. So I'm going to ask you to pause the video shortly. Try and scribble down some answers. They do get a bit tricky once you get down to the bottom ones, okay? But don't just chicken out and wait for me to go through the solutions. Give it a good 10 minutes like you would in class, please. And then we'll talk about the answers shortly. So please pause the video now. Here are the answers to the first few questions on the last slide. There's the symbol for momentum. It's rho, very similar to the symbol for density. Momentum is mass times volume. So for the first one, multiply them together, you get 7,500. The second one, multiply them together, you get 7. Number 2 was a bit of a daft question because you're working out the weight of a rugby player. And for some reason it comes out as 5 kilograms. It's a very, very small rugby player. Number 3, let me click back. It won't let me. Number 3, momentum is conserved. We'll talk about elastic collisions later and the conservation of momentum. But effectively, for an elastic collision, all momentum before equals all momentum after. Number 4 is a simple product again, the mass times the velocity. Be careful with the units here in your standard form. Question 5 is the one that's going to cause most of the pickle. It gives you the density of water, which you should already know. It gives you the cross-sectional area of the hose pipe it is flowing out of and how much, or the volume, per second. How much momentum is carried by the water leaving the hose per second. Now it tells you what the answer is, you just had to get there. Now of course, as momentum is mass times volume, the first thing mass times velocity, the first thing we had to do was work out the mass of water coming out. So the mass is the density times the volume. There's the density, there's the volume per second. So that's the mass of water coming out per second, 200 grams or 0.2 kilograms. The meters of water coming out per second would be the amount of water, that volume, divided by the cross-sectional area. That was the bit you had to really think about there. So that's how many meters of water are coming out per second, 0.27 recurring meters per second. And then of course you can use that as your velocity, you can use that as your mass, and that will give you the momentum when you do the product of those of 5.6 times 10 to the minus 2. Notice the change in units there. I've now decided to call my kilogram meters per second as Newton seconds. Okay, talk more about that later. And question 6, the football match 1. Calculate the change momentum of the football. Well, it was stationary, so its initial momentum is obviously 0 because its velocity was 0. So it was just mass times velocity, and that's its new momentum, 14.08 kilogram meters per second, or Newton seconds. Now the main part of this unit is as follows, okay? When bodies in a system interact, the total momentum remains constant. provided there's no external forces acting on the system. In a nutshell, if you have two objects hitting each other, the total momentum before the collision will be equal to the total momentum after the collision. And we can use that fact to work out missing velocities, okay? So here's a basic example. I got a lorry there going 30 meters per second, and it weighs 10 tons, 10,000 kilograms, and it goes into the back of a car. They're both traveling in the same direction, but the car is traveling slower at 12 meters per second. And they coalesce, okay? It says find the speed of the vehicles immediately after the collision if they remain jammed together. Now that if they remain jammed together is called coalescing, and now there's a combined mass of the two objects traveling at one velocity. All momentum are considered in the direction of travel. So before the collision we have the momentum of the car was its mass times velocity is that. The momentum of the lorry was its mass times velocity, which is that. So the total momentum before the collision, add up those and you get 318,000 Newton seconds. And momentum is conserved, Sir Isaac told us, and we must believe him. So the total momentum after the collision will also be 318,000 Newton seconds. Now the total mass after the collision now is the 10 tons plus the 1.5 tons, which is 11,500 kilograms. So the new velocity will be the momentum divided by the total mass, which comes out as 28 meters per second. And of course they're both going in that direction of travel there, from from right to left. So the lorry has slowed down a bit and the car has sped up significantly. So I'd like you please to have a crack at this question. Okay, this time I have a 2,000 kilogram van and a 1,500 kilogram car, both traveling at 40 but in opposite directions, right? So let's have the van going left to right that way, and let's have the car going right to left that way. And of course, because velocity is a vector, they'll have opposing polarity of velocity. So let's call the van positive and let's call the car negative, okay? Work out the total momentum before the collision. They lock together, which means they coalesce, so you have one combined mass, and then you can work out the velocity after the collision. So please pause the video now and give yourselves 4 or 5 minutes, draw a little diagram and have a go at that question. Okay, thanks. Right, so here's the solution. So here's my 2-ton van going 40 meters per second left to right. Here's my 1.5-ton car going 40 meters per second from right to left. Okay, so before, the total momentum is that times that minus that times that. Okay, so the total momentum before is, what's that, 80,000 minus 60,000, which is 20,000 Newton seconds. So that's the total momentum before the collision. And the reason it's a minus, don't forget, is because this is traveling in the opposite direction. Now the total momentum after the collision will be the same. It will still be 20,000. So we can now work out the new velocity. The two vehicles have coalesced, so that we now have a total mass of 3.5 tons or 3,500 kilograms. So to get the velocity of that new system, I get this 20,000, I divide it by the 3,500, and I get 5.7 meters per second. Okay, so they both slow down significantly, and the heavier van has won the battle, and they're going left to right. Now momentum is very significantly related to Newton's laws of motion, especially the second one, F equals mass times acceleration, because acceleration is the rate of change of velocity, so therefore force, as mass times velocity is momentum, force can be defined as the rate of change of momentum. Okay, hugely important. So force is the rate of change of momentum. So that's mv minus mu all divided by t. And let's talk about how it works here with this rocket. The diagram below shows a rocket attached to a trolley, total mass 50. It accelerates from rest along a horizontal track and reaches a velocity of 120 in a time of 8. Assuming there's no friction, calculate the force produced by the rocket engine. So I'd like you to do it the first method just using some basic SUVATs and F equals ma, and then method 2 complete it by using force is the rate of change of momentum. And of course you should get the same answer both ways. So please pause the video for 2 minutes and quickly rock through that question. Thank you. So if I use some Newton's second law and some SUVATs, F equals ma, and a bit of V equals U plus AT to get that acceleration, I'll get 750 newtons, which I'm sure you did. And of course, if I just use force as the rate of change of momentum, you can see the embedded is the V equals U plus AT rearranged, so you get the same thing of 750 newtons. Okay, so either of those methods are fine. Now this is a cracking question, and this will be the last one for part 1 of the lesson. This will be on your assessed homework as well, so make sure you understand how we do this. Diagram below shows a hose pipe which is directing water horizontally at a wall. The mass of the water leaving the hose pipe is 1.6 kilograms. It strikes the wall with a speed of 12 meters per second. The water then just dribbles down the wall. It does not rebound. Rebound or rebound, I'm not sure how to pronounce that there. Calculate the force on the wall. Right, so force is rate of change of momentum. If the water did rebound, bounced back with a speed of 2 meters per second, what would the force on the wall be then? And explain why the force is greater in part C, I think it means B, than in A. So why in this answer is the force greater than this one? Okay, pause the video. You're going to find this quite tricky to start with, and I'll go through it shortly. So give it a pause now, please. Right, here's the solutions to this question. Okay, calculate the force on the wall. So the initial velocity is 0, but when it hits the wall, it's going at 12 meters per second. Okay, now the mass of water leaving each second is 1.6 kilograms. So in 1 second, we have a mass of 1.6 kilograms. That was the tricky bit there, just figuring that out, right? Now chuck it all into force's rate of change of momentum. And we've got the mass times the velocity. Got these the wrong way around, haven't I? Do apologise. When it leaves the hose pipe, it's 12 meters per second. When it hits the wall, it's 0. So I've got my U and V wrong way around there. Chuck it all into the rate of change of momentum equation, and the force is 19.2 newtons. Now, if the water rebounded with the speed of 2, what would the force on the wall be then? So we've got the maths, 1.6. We now have a new speed of 2, but in the opposite direction. 1.6 times 2 is 3.2. So the resultant force now would be a 19.2, subtract that rebound force of 3.2, which gives you 16 newtons. And why is this force bigger than this one? And that's, of course, there's a loss of energy due to the sound and heat of the water hitting the wall. And that's quite a popular question, that one. So spend a few seconds getting your head wrapped around that. Now this is coming up to my allotted 15 minutes that I'm allowed to post on YouTube, so I'm going to stop it now and then start part 2 of the lesson. Okay, so bye everyone.